In the second part of this tutorial, we want to compute the Laffer curve, which you can see in the slides. So for this reason, we will go into the MATLAB code. You need to have a running version of MATLAB. You need to download the MATLAB code from my home page. In particular, you need to place 3 files in the same directory. Laffer.m, which is the MATLAB code, and 2 auxiliary files, which are Excel files. One is called efficiency profile.xls, where we have stored the Hansen age efficiency profile, so where households, workers at the age of 50 have the maximum productivity and afterwards it declines. And we also need to load data for the demographics, for the US demographics, and this is provided in the file. Let me just check here for a second. In the file survival props US XLS. So please make sure that you store all these 3 files in the same working directory, and I would like to ask you to open MATLAB. If you have no prior or little experience with MATLAB, it might be useful if you go through the tutorial that's provided by MATLAB, or that you start with easier programs from my chapter 3, where I have some simple applications with just a few lines of codes. So let me switch into our MATLAB program. Right in front of you, you should have a screen something like this, and you should have loaded the file Laffer.m into your directory and opened it in your workspace. This program computes the Laffer curve. And first thing you should always do when you load my programs or any code into your editor, just run and see if it works. So just press run, and you will see in the command window that the MATLAB is computing something. So for example, if you see an NH equal to 53, 54, that's the OLG model with 54, 55, and so on cohorts. And shortly it will finish and will run up to a maximum of 70 cohorts, and next it will add the endogenous labor supply to this, and finally the computer code will compute the Laffer curve, and the output should be seen shortly. So this is the figure 4. This is the asset behavior of the individuals in the case of a 70 period overlapping generations model with endogenous labor. So you can see the hump-shaped profile of the assets. So they start at age 20, households start with 0 assets. Maximum occurs shortly prior to retirement at age 60, and then they decumulate their savings. The increase in mid-age between 30 and 50 is a little steeper than prior or after this. This is in accordance with the age efficiency profile. So in the early years, workers are not as productive as in mid-age, and therefore have lower income from which they save. Another output from this program is the cohort mass. So we normalize the cohort mass to 1, that the sum of all cohorts is equal to 1. So you can also interpret the cohort mass here as the share of the population in stationary population. So the 20-year-old have a share of 0.022, so about 2.2, 2.3%, and it declines slowly as agents die with a certain probability and only survive with a probability below 1, and the population growth rate is also below 0, but this effect, as we will find out, these two effects together will result in a decline in cohort mass age profile. In Figure 2, this is the age efficiency profile, the individual productivity over lifetime, which is loaded from the Excel file efficiency profile.xls, which is a profile estimated by Hansen. So you can see that maximum productivity is attained at age 50. We have two kinks in the behavior at age 30 and 50. So this will result also in kinks in the behavior of labor and consumption. And we have the annual survival probabilities that we load from the file survival props US XLS, the Excel file. And as you can see, they monotonically decline from almost 1 to about 0.89 at age 89. And at age 90, the probability is 0. So people die for sure after a life of 70 periods, of 70 years. Now let's go into the program code. And the program code is structured in 8 parts, in 8 steps. So as always, I introduce a little comment in the beginning where I explain what the computer does, the code does. So it computes the Laffer curve, who's the author, and when the last change was done. So in case you want to modify the code, I advise you to save it under a different name, and so that you do not lose this original code that works. So, and I clear the screen and close all variables so that there are no other variables sit in the memory and will lead to misleading results. In the first step, I parameterize the model as in Trabant and Ulich. Let me go through the steps quickly. In the second step, I load the data from the UN population data, so file survival props US XLS. So please make sure it's stored in the same working directory. And also load the efficiency age profile from Hansen. So make sure that the file efficiency profile.xls is also stored in the same directory. In the third step, we initialize the capital H profile and the aggregate capital stock. In the fourth step, we compute the simple model with 46 periods. So we have workers over a time horizon of 45 years, and in the final year of the life, agents retire. So this model behaves very close to the Ramsey model, and we can use the aggregate capital stock from the Ramsey model as a starting value for our aggregate capital stock, and this helps tremendously in the computation. And once we have computed the 46 period overlapping generation models, we go on and increase the number of periods by 1 in each step. So add another cohort, an additional cohort of retirees to the model, and use the solution from the previous model as an input into the new model. And this converges nicely to the 70 period overlapping generation model with exogenous labor. In step 5, we add endogenous labor, and our initial value for this endogenous labor will simply be the exogenous labor that we had assumed so far. And in the step 6, we also endogenize the aggregate variables. So in particular, we set up a procedure SS aggregate, which uses as input x0 the individual capital stock wealth age profile, the individual labor supply, which we have computed before, and then the aggregate variables capital stock, labor, the capital share in total assets, the social security contribution rate, and the transfers. In step 7, we calibrate beta, and therefore we add one additional variable to our endogenous variable x, which is the discount factor beta. And in the procedure SS aggregate calib, we compute the solution to this nonlinear equation problems. And beta will be calibrated such that the rate of return, the real rate of return on government bonds is 4%, as in the model by Trabant and Ulich in the JME 2011. And in the final step 8, we compute the Laffer curve. So we use our previous calibration of beta, which also implies our benchmark government consumption, big G in our model here, and our government debt, big B. Both these variables remain constant when we compute the equilibrium solutions for different values of the wage tax tau n, which goes over space, over grid from 10% to 90%, and we will store the results, the labor income taxes, or to be more precise, the wage taxes and total taxes in our variable results, which we display in the completion when we complete this program. This program code, as you will find out, is rather lengthy, so a couple of 100 lines. I could have programmed it much more economically, bringing it down to perhaps 200 lines. But more often than not, to this rather simple program technique that I apply is much easier to comprehend if you are not very sophisticated and used to the use of MATLAB program. So if you are starting to use MATLAB code and getting only familiar with it slowly at this time, this will help you to debug and go through the program step by step, and will be hopefully much more understandable than much conciser, neater code, but nevertheless more complex code. So let us get into the program and debug it. For this reason, place the cursor on the minus sign in line 17, click, and you will have introduced a breakpoint, so-called breakpoint. If you now press run, the computer code will be executed just up to line 17. Hopefully. Let's see. We have not finished the final run. Okay. Here we have the Laffer curve. Sorry, I did not finish the previous run. So here you see the Laffer curves as our final result. And now we have started the new execution of the code Laffer.m, and we are in line 17. Here we parameterize the model as in Trabant and Ulich. So we set the coefficient alpha, the production elasticity of capital, equal to 0.35, and now press step to proceed to the next line. You can use the arrows in the upper menu bar to move around in the code now. Delta is set to 8.3%, the depreciation rate. The annual real interest rate on bonds, which will help us to calibrate beta, is set to 1.04. The initial guess for our steady state labor supply, individual labor supply, is 0.25, so agents are supposed to work 25% of the time. We will find out that in our computation for the preference parameter kappa 3.619, that is copied from Ulich, our labor supply will be 0.31. So if you want to get closer to L bar of 0.25, you should adjust kappa, but we are happy with such a value. So in dynamic general equilibrium models, in the Ramsey model, we often target a value of average labor supply of 30%, 33%, or 25% of the of total time. So this is what we're looking for, and it shows that we can also use Trabant's and Ulich's calibration for the Ramsey model here, in our case of the overlapping generation model. We set the growth factor equal to 1.02, so a growth rate, annual growth rate of 2%. And this is of course important effect for pensions, consideration of pensions. The return of the pension system of your individual contributions of course depend on two growth rates. One is the economic growth rate and the other the population growth rate. For a higher economic growth rate, it means that future generations, future young people, pay higher wages, which will be distributed to you in a pay-as-you-go pension system, so you profit from this. And of course, if there are more of them, if you have high population growth, this will be also distributed to fewer retirees, meaning that each one gets more. So the return from the pay-as-you-go pension system depends on these two numbers: the economic growth rate and the population growth rate. And of course, in the United States, this is much more beneficial than in, for example, countries like Italy or Germany. Now we set the fresh labor supply equal to 1 in accordance with Ulich. This is rather high. So this is more on the upper limit of the interval for values that are used for the fresh labor supply elasticity. Of course, it helps us to generate a nice result for our Laffer curves because labor supply is more sensitive with respect to taxation. And we set the intertemporal elasticity equal to 1/2. As our initial guess for beta, we use the growth rate to the power eta divided by the gross interest on government bonds. Now to derive this, we look at the Euler equation with respect to government bonds and find that if we have constant stationary marginal utilities, tilde lambda, our Euler equation boils down to exactly this condition which is stated in line 32. And as a first approximation this will do. Later on we of course calibrate beta so that the real return on government bonds is equal to 4%. The initial labor income tax is 28%, so this is the wage income tax tau n plus social security contribution. We have capital income tax equal to 36%, consumption tax equal to 5%. We set the social security contribution rate equal to 12%, so that's close to the US value. And of course it will be endogenous later on, so that the social security contribution rate balances the budget of the social security authority, so that aggregate pension payments are equal to aggregate social security contributions. The debt GDP ratio is copied from Trabant and Ulich, 63%, and seems low in comparison to today. So if you want to find out, well, how does a higher debt level in the US today affect our Laffer curves, just set this level equal to 100% and go through the steps again. And we also use a government consumption ratio of 18%, a replacement ratio of pensions, so pensions relative to gross labor income of 35%, and these three parameters are numerical parameters which determine the accuracy of our nonlinear equation solver and the number of maximum iterations over the capital stock, and phi will be an updating parameter which we will explain in the following, later on below. And we also use alpha, delta, and so on as for notational convenience. This parameter par here, the structure, we will pass it on to our function that we call, and to make our notation a little bit less cumbersome, in the main program Laffer.m we also assign the value alpha to par.alpha and so on. So press step to go on with our calibration here. In line 69, we set the number of 5-year periods to 15. We will need this to convert the 5-year survival probabilities that are provided by the United Nations into annual periods. RH, oops, oh, sorry, now I, I went through the whole program, so let me restart here, quit debugging, and go back to our to the line where we just finished. Sorry for this inconvenience here. So I place a breaking point here in line 66. Not in line 66, in line 66, where we just 65, where we just stopped. So let's run again and go to line 65. So we set the year equal to 2010. This is our benchmark year. And when you want to use other years, upcoming years, for example, if you want to see how the Laffer curve reacts to the demographic transition, you just change year 1 here to a year, let's say 2050, and the program will be able to compute the new Laffer curve, and you will be able to compare it and see that the fiscal space will shrink in the United States because of the aging process. You can also find some material on this in my book on public economics in chapters at the end of chapter 6. So we stepped into the next line. We have 70 periods in our final model, and this is also stored. RH46 is the first period when agents retire. NR is our number of retirement years, which amounts to 25. NW is 45, which are the number of working years. And we also store this in the structure par. And we use the case UN scene equal to 1. So this will mean we use the medium scenario. For the year 2010, this doesn't make any difference whether we use scenario 1, 2, or 3, because all the scenarios are the same. But if you want to evaluate the case for a year, let's say 2050, the UN provides you with 3 different projections: a medium, a low, and a high version of fertility. And depending on which version you choose, you have a different forecast for the demographics and, as a consequence, different Laffer curves. You are free to experiment around with these different values when you play with the code. So this concludes step 1. Now let's get to step 2, where we load the survival probabilities from the Excel file survival props USL XLS. And they will look like this: columns 1 through 11. Since the survival probabilities are stored in a rather unconventional way, starting with the oldest and going up to the youngest, we have to reverse this order with the command fleetput. So if you do not know a particular command, what you can do is you go into the menu point home, use the help function, and type in perhaps a command that you do not know, fleetput. And here it tells you what it does. It flip array up to down. So it reverses the order in a vector here in our case. So let's go back into the editor and press step to go to the next line. Next we read the population growth rates. The population growth rate looks like this. 1.581, 1.581, 1 and so on. And these are the population growth rates for the different three scenarios. So 1.58 is the population growth rate in 1950 and for the three scenarios. And notice that in the first years these numbers are the same for each scenario, and only in later years starting in column 14 here with a value of 0.719, 0.556 and 0.880. So the medium population growth rate projected for the year, I think this year 2020, is 0.719, and the other two are the low and the high volatility scenarios respectively. And you can also look at these time series in the matrix n rate, where the year on the left hand side, so 1950 in the first row, provides you with a population growth rate of 0.16% and so on. And in the year 2040, the last line in this displayed for this matrix 2040, we have a projected population growth rate of 0.04% with low volatility scenario of 0.01 and a high volatility scenario of 0.07. In the next couple of lines, we use a moving average to get a more smooth behavior of our demographics data. So for example, if we consider the year 2010, what we will do is we construct a moving average from the year 1990 to 2010 of the population growth rate and survival probabilities. And this is done in the next 10 lines. So jump to line 101 and use run to cursor. Place your cursor in line 101 and press the arrow run to cursor to skip this computation of the moving average, which are, I think, self-explanatory. Notice that I have to divide population growth, the data from the United Nations, by 100 because they were given in percentage terms. Okay, so we step on, we display this stuff. So population growth rate for our year 2010 is calibrated to be 0.95. Let me also add that we used this 20-year moving average window because Trabant and Uhlich calibrated their model for the period 1990 to 2010. So they used exactly the same calibration period, and we want to be comparable to their study. So the population growth rate is 0.95% in 2010. We store this in the variable GN, so growth rate of population. And we also use now the survival probabilities here which are given for 5-year intervals to annual periods. We do this by using an interpolation scheme that's provided by MATLAB. So the command interp1 means that we interpolate a function in one dimension, so which is our function, the survival probabilities, as a function of age. We have grid points which are spaced at a distance of 5 years, and this is given here by age, the variable age, and we have the original data SP, which are our survival probabilities over a period of 5 years. So for example, in the last entry 0.54 means that the individual at this age survives with another 5 years with a probability of 54%. Now we want to interpolate this at the grid points H1, which are annual grid points. So it's a vector going from let me step there, from starting at 20, going up to 90. So all the ages in our overlapping generation model. And we want to interpolate the survival probabilities at these grid points, and we want to use a cubic spline method. And so not just a simple linear interpolation, but much nicely a spline, so taking care of the concave function, of the concave form of our function survival probabilities. And in line 120 we convert the 5-year period survival probabilities to annual periods and save them in the vector spar. And next we just plot these variables, our survival probabilities. And this gives us the nice graph that you have already seen. And in our second step, in our second part of this step, we load the age efficiency profile, normalize it to 1, and save it in the variable EF for efficiency. So we also plot this function, and let me show it to you again so that you get an idea how it looks like. It is characterized by 2 kings at age 30 and 50. And finally, in this step, we compute the share of each population here, of each age group. And for this reason, we iterate over the mass of each cohort. So the number of t-year-olds is equal to the number of t minus 1-year-olds times the survival probability divided by 1 plus the population growth rate. I have written down a small explanation for this formula here in the comment in line 146 to 154, and you may go through it to understand why we use equation 1 in line 157 to compute the mass. We normalize, let's jump to line 159. We normalize this mass by setting the sum equal to 1. And we save this mass in the vector mass initial. So the initial 20-year-old cohort has the share 2.26% and so on. And as you can see, the share of the aging cohorts is declining. And we can also plot this result here, this vector mass as a function of age declining with age. Tick starts the computational time so that we can measure how long it takes to compute our model, and we now get to the meat of this program in line 178. And this is the initializing of our simple overlapping generation models with 46 periods, 45 cohorts of workers, 1 cohort of retirees. And what we do is we assume that this model behaves very similar to the Ramsey model. So if you look at it, it's a long time horizon, 45, 46 periods. The household is always working except for the last period, so just like in the Ramsey model. So why shouldn't the average capital stock be much different from the capital stock in the Ramsey model? So therefore we use the capital stock from the Ramsey model, and this follows from the Euler equation of the Ramsey model, which you should be familiar with. And it's of course the same if we set our Euler equation with respect to capital, use our Euler equation with respect to capital, set all the Lagrange multiplier, the lambdas equal to each other, so that they drop out in this equation. So we can relate our real interest rate from which is equal to the marginal product of capital to beta. And for beta, we substitute from the Euler equation with respect to the government bonds. And this results in equation 180 for the capital stock. So here you can, and we also set the average labor to 30% and the aggregate labor. So all of our cohorts except for the last one are workers. Everyone is working, and we assume an exogenous labor supply of, let's say, 0.25 or 0.3. So why shouldn't be the aggregate labor supply equal to 30%? Seems like a good first initial value. You can also set it to 0.25, so it will not change anything. It's just initialization here. And we store this in the column vector x. In the vector x. Okay. We compute the wage rate and the interest rate. For this, we have used the two functions, wage rate x and interest rate x. And we also compute the production x. Let me step into this procedure here. Y bar is equal to production of x and par. This is the same for the wage rate or for the interest rate. What we pass on are two variables, x, which is our capital stock and our labor, and our structure with all the values, for example, the production elasticity alpha or the depreciation rate delta. And this helps us to compute the production here, or in case of the wage rate, the marginal product of labor, in case of the interest rate, the marginal product of capital as our return. So we have computed this for our input here as y equal to 0.1601, and this will be returned to our calling function here, y bar, so that it is stored in the variable y bar. With the help of aggregate production, we can initialize here government debt, and which is 63% of output. The initial capital share in total assets and total wealth. Total wealth is the sum of capital plus debt, plus government debt. And we use as initial value for transfers, we use 1% of output. We will find out that it's approximately 5% in our final model, but it doesn't really matter much how closely we initialize this. So if we use 2% or 0%, it all will work out fine, and the computer code is rather insensitive with regard to this assumption. Also with regard to the pension, we just use any value here, 0. We use the same as tau p, our social security contribution rate, 0.124. We can also set it to any arbitrary value. Perhaps it would have been easier to set it to tau p times the wage rate times L bar. So you may check this if you like. Okay, and now we get to step 4. Now we have initialized this particular problem. We have chosen values for the aggregate variables, and we want now to compute it for number of model periods starting from 46 up to 70. So this is specified in the vector NH grid, and we start with the first case for our 46 period model, and these variables are also stored in the structure par, which we will pass on to our procedures. We will compute the stationary mass of the population here. So let's go to place the cursor on line 230 and run to this line. So this is our mass here, and as you can see, the share of the 20-year-old has increased to 2.78% because we have fewer generations in our model. We store the optimal policy function, the asset, the savings in A opt, the consumption C opt, and our labor supply in N opt. and as we consider the exogenous labor case first, we set labor supply to 25% for each working cohort, and this will only be adjusted in the next step. So now we start with the first model with 46 period and IH equal to 1, meaning one retired generation. So now we have to choose for the first time initialization of the optimal policy function of AOPT for our individuals. So we are planning that our model implies the same capital stock, average capital stock as the Ramsey model, K bar. And we know from the study of overlapping generation models that our households build up savings gradually. So they start with 0 savings at age 20, then they increase their savings over a lifetime, and shortly before they retire, they start to reduce their savings. So let's assume that the maximum savings is in the last period of their working life, so at age 64, and at age 65, when they retire, they start to decumulate. This means that if we assume, for example, a linear increase over a lifetime of the capital stock, it makes sense to set the final wealth at age 64 in the final period of the working life to twice the capital stock of the Ramsey model, and assume that they linearly increase their savings over the working life and also linearly decrease it over their life as a retiree. And as a consequence, our initial capital stock is specified just like in our variable K initial. So let's look at K initial here. We have a K max equal to approximately 0.1. This means that over the working life, the capital stock amounts to 0.12 in the last period of the working life at age 64, and then it drops to half, so to 0.1 at age 65 and to 0 in the last period. That's how we initialize it, and it seems like a very intuitive way once you know that how overlapping generation models work and what kind of result they generate. So this is actually the problem, how to come about. If you have a very complex problem, you do not know where do I get an initial solution, that's how we do it. We start with a very simple model where it's intuitive, where we have an easy way to figure out how the initial policy function might look like, and then we build it up to a more sophisticated model. So for this initial value here of our assets, it's a variable with 45 entries, a column variables with 45 entries. So the 20-year-old, which corresponds to the first cohort in our OLG model, starts with 0 assets. So that's why we exclude this. This is already given as exogenous. And at the end of age 1, at the beginning of age 2, which corresponds to real life age 21, this asset his savings have accumulated to 0.0022. And this vector therefore contains also the capital stock, the asset at the beginning of age 65. This is the last entry of this column vector, and in the next period we know assets are equal to 0 because the person has died. So now we step into this procedure as exogenous labor. We pass on this capital stock, this asset profile to be more accurate. It's both capital stock and government bonds, the sum. And we pass on the parameter here, the structure. So for example, we know the total number of periods NH is equal to 46. and the output will be a variable y, which needs to have the same number of entries, so 45 as the calling variable here, as the endogenous variable 45. Of course, if we want to solve a nonlinear equation system in 45 variables, we also need 45 conditions equation, and these will be stored in the variable y. The next 3 lines are just to check if everything is, if it's fine. So I need to use vertical vectors, so use column vectors all over. Sometimes your computer code bugs because you use row vectors instead of column vectors, so be careful to watch out for this. And again, we use short form for the variable par.taup. We just use taup as a local variables here, so to make our code a little easier and not so cumbersome and clumsy and easier to check. So in the variable asset, we include the starting asset of 0. So the newborns have no wealth, and also include the final asset level of 0 when you are dead. We will use this to make our Euler equation much easier to formulate with the help of the vector asset. So the exogenous variables, aggregate variables, are the share of the capital stock and total assets, and the remaining share are held in the form of government bonds. We know that the labor supply is equal to 0.25 in every working period, and now we compute, and we also add a 0 for those aged, for the retirees. So labor S contains the labor supply of the young cohorts, of the working cohorts, and the 0 labor supply of the retirees to make the code much easier to be formulated in terms of these 2 variables here, so that we do not have to distinguish, for example, the computation of utility or marginal utility for the workers and the retirees respectively. And next we compute the individual consumption here over line 75.9 through 6.2 for the workers first. So here we have the net wage, which is simply wage income times the individual productivity times the labor supply. And of course, net wages are the labor income taxes here, which consist of tau n, the wage income tax, and tau p, which is the social security contribution rate. Second source of income is capital income from holding capital stock, so the return D bar on the capital stock minus depreciation, so depreciation is tax exempt, and the return from government bonds, so the gross return here 1.04, and we have to also use stationary variables. That's why here the growth factor shows up in front of next period capital stock and bonds, and we have to acknowledge a consumption tax of 5% for the United States. And similarly, we can compute this let's run to further in line 764. We can compute the consumption from the budget constraint of the retirees. We simply have to replace the net wage income by pension income. And we also have to distinguish the final period of life here, because in the final period of life we do not build up capital stock or bonds holdings for the next period when we are dead. That's why this constraint here is a little shorter. So now we have computed the consumption vector with the help of the initial value of the asset holdings of the households, and we can formulate the intertemporal first order condition, which is the Euler equation. So the Euler equation is given in line 777. This is the stationary version of the Euler equation, and here you can see in the formulation, we pass on the variable x0, which is the consumption and labor, to the procedure UC, to the function UC, where we compute the marginal utility. And for this, it was convenient to formulate labor also for the retirement agent and set it equal to 0, so we do not have to make any fuss here and distinguish between the cases of workers and retirees in this equation. And here you see simply the Euler equation with respect to capital. This will be our first order condition that we pass on. And when we have computed these first order condition so in the first case it's minus 0.4456, so it's a little bit off of 0. We're now looking for the solution so that these Euler equations here in line 777 are equal to 0. So let's step out of this procedure and start to compute it. This will be the inner loop in step 5, and the outer loop is over the capital stock. So we've started with initial values for the aggregate capital stock K bar and aggregate labor N, and we have also values for the transfers and the tau P. Now we go on for these values, and in line 298 we compute the solution to the nonlinear equation in the procedure SSX exogenous lab that we just looked at. So we want to find the root x here that gives us the solution to this initial value problem. Okay. And here we have the solution xf. This is the solution to our nonlinear equation problem. So the optimal asset level is equal to 0.0297 at the age 20, 0.0676 at the age 21. If we assume exogenous labor and a capital stock equal to 0.0499 and aggregate employment of 0.3. Okay, but now we have to acknowledge that these, of course, are not the equilibrium values implied by our individual optimization behavior. So what we do is we compute again the consumption, just like we did in the procedure. So let me skip over the line 316 to the line 332, run to Curve. We have meanwhile computed the optimal consumption for this capital stock. And what we do now is we use the aggregate consistency condition with respect to capital to compute the new capital stock. So we know these are the individual savings of our households at the beginning of age 20, 21 and so on. We know that this is the share of their households, their mass, and if we multiply assets times the mass, we get the new aggregate capital stock. Aggregate wealth level. We get the new aggregate capital stock by multiplying with K share. So we have the new capital stock equal to 9.2531. We have the old capital stock equal to 0.0499. So what we do next is we update the capital stock and use an updating scheme, a dampening scheme that's copied from Judd 1998, Numerical Methods in Economics. So we use the old value, 90%, 10% of the new values. So this gives us the new capital stock 0.9702. And from this, we also compute all the other endogenous variables. So for example, we use our optimal consumption behavior to compute total consumption. This gives us the consumption tax tau c times big C. We have the new capital stock, which gives us the capital income taxes, tau k times d bar minus delta times k bar, and we have our value of wage income taxes. We can also compute the bequest, the accidental bequest, with the help of these optimal savings of the households. So this gives us the revenue of the government from taxes and from bequests. And we can also compute the expenditures, which consist of government consumption, big G, also the expenditures on the interest rate payments on government debt, big B, and the residual from the revenues, taxes plus bequest minus government consumption and interest on government bonds results in a new value of the transfers, and we will use this to update transfers in line 350. So let's run to line 350, where we compute the new transfers. And we also compute the new effective labor supply. So effective labor supply now, as you can see, the new value is 0.2422, is much lower than our value 0.3, which with the one we started. And well, of course, our exogenous labor supply is 25% and almost all are working, so 25% would have been a much more accurate starting value. But this will converge nicely to this value, so don't worry if your initializing is not 100% correct. And we also use the values of K share to compute a new value of the capital stock, and we also update our value of beta. So we use the two Euler equations with respect to government bonds and with respect to capital. From the Euler equation with respect to government bonds, we get a value of the lambdas, the ratio of the lambda divided by 1 plus the growth rate to the power either. And we substitute from this and into the Euler equation from capital stock, and this results in a new value of beta nu, and we use this new value of beta nu 1.60 and substitute it in our guess for beta 1, just updated it by 10%. So 1 minus phi equal to 10%, and save beta. We also have to compute the mean labor supply, which is the product of the age efficiency times the working hours, and this will be used as an input into the computation of the pensions, which are simply replacement ratio 35 of average gross wage earnings, which are wages times productivity times labor supply hours, and this new pension now amounts to 0.03. So as you can see, our first initial value was way off, and we will update pensions now and the social security contribution rates in the next couple of lines. So our social security contribution rate is the pensions times the number of retirees, which is given by this sum, divided by aggregate labor income. So aggregate labor income times times social security contributions is equal to total payments on pensions. This is just the social security budget constraint, and in lines 368 and 369 this parameter here is updated. Also in lines 371, 372 the parameter, the variable pensions. And so we have two loops here. The first loop is over the aggregate capital stock, and when this loop has converged, we have computed in the first iteration the 46 period overlapping generation models with exogenous labor supply, and then we increase the number IH by 1, the number of periods in our model. So next is the 47 period model, and then again we we iterate over the aggregate capital stock, and we always use the input from the previous model with one period less into the next period. So if you go all the way up here into this loop IH from 1 to NR, what we do, we have to recompute the new mass of each cohort, because we always have an additional cohort of retirees which change the masses, and we have to provide a new value for our initial capital stock. So if we include another cohort of retirees, we just assume that they have half the asset level of the oldest generation in the previous computation of the overlapping generation model with one less generation. So if we go from a 46 to a 47 period overlapping generation model, we now assume that the generation at the beginning of period 47 have half the asset level of those in the last model at the beginning of age 46. And the rest is simply keep on iterating over the aggregate capital stock and over the number of periods. So this will get us to line 398. So let's run to cursor line 398. I have to delete the breakpoint here, run to the cursor, and put the cursor in line 398 again, run to cursor. So now we run through the case with exogenous labor and 46 up to 70 periods and run to line 398, where we just display the figure and the optimal behavior of our households with respect to savings with the accumulation of wealth, which is stored in the vector A opt. And you know this picture from before, I've shown it to you. This is simply the optimal savings behavior of our household, of our 70 period overlapping generation model when agents die at the end of age 89. So we almost through. This was the longest part. From now it's not, the rest is easy. We have to introduce endogenous labor supply in step 5, and we just assume that everyone is supplying labor supply of 0.25, and we have to add this gas in our initial value here, because now we have to solve an endogenous system of 69 plus 45 variables, which is stored in the function SS endogenous labor. So let's step into it, and let me just show you what has changed. It is the same as with exogenous labor, except for these 4 lines here, where we include the efficiency condition with respect to the optimal labor supply. So this is the first order condition of the household, of the working households with respect to labor supply, 45 equations, so that the marginal utility from the income that is provided by working another extra hour is equal to the marginal disutility from labor, and this is condensed in this equation in line 85, where you can see here the marginal product of labor times the efficiency and the disutility of and odds from working versus the marginal utility from consuming an extra unit. So let's step out again here, and we just iterate over this endogenous labor steady state conditions which contains all the individual variables as endogenous variables and all the aggregate variables as exogenous variables stored in the vector par. So here, for example, par, you find the value of L bar equal of wow of let's see. So for example, the value of the pension or the value of beta and so on stored in of transfers and so on stored in the structure part. Okay, and we have to iterate again over the capital stock and the aggregate variables, and this provides us with a solution, and all these solutions are again stored in the structure par and in the appropriate aggregate variables. Now in step 7 we need to calibrate the model. So let's take a look into this new procedure, SS aggregate calib. So go to line 547, run together. And now let's step in and I will show you what's new in this function. So in this function we have passed on the aggregate variables car bar for the aggregate capital stock, aggregate labor n bar, aggregate debt, aggregate social security contribution rate tau p, aggregate transfers transfer bar, and beta as our endogenous variables. From these variables we compute, for example, the labor income tax, which is given by our calibrated variable tau L bar equal to 28%, which is equal to the sum of the social security contribution rate and the wage income tax. We compute the capital stock, the capital share, and so on. And let me show you some new entries, and the new entries are starting in line 1089, where we add the aggregate consistency conditions. So one new consistency condition is that the endogenous variable k bar is equal to the aggregate capital stock, which results from summing up all the individual capital stocks. Similarly, then we have these 4 aggregate conditions here, that the transfers provided in our endogenous variable is equal to the transfers which follow as a residual from our fiscal budget. Our aggregate capital stock n bar is equal to the sum of the individual labor supplies. Our endogenous variable tau p for the social security contribution rate is equal to the variable tau p new, which balances the social security budget. And similarly for debt, that it's equal to the individual savings in the form of government debt. And finally, this is our equilibrium condition for the calibration of beta, that the return from savings in capital is the same return from net return after taxes from saving in government bonds. So when we step out of this procedure, this is a procedure where all equilibrium conditions are fulfilled simultaneously. We are looking for the solution of this nonlinear system. If we had started with this, why not start with this? This is a big question. No? Why not use SS aggregate calib right from the beginning? Well, the problem is to provide this initial value here, x0. That's why we are doing all this, to have a 120 and to assign a value for the initial value of this 120 endogenous variables. Only if we get somehow close to the true solution, we find we have a good initial value and good enough initial value to find the solution with our Gauss-Newton method, with our fsolve routine. Otherwise, this will not converge. That's why we go through all the trouble to start from the 46 period model, go up to the 47 period model, and so on, introduce endogenous labor, and then finally introduce all the endogenous aggregate variables as well. So in line 55.1, we compute the endogenous variable. As you can see, this takes just fractions of a second, and we have found the final solution. And from this solution, we store all the equilibrium values here as our benchmark values. We store beta 1 as our calibrated value of the discount factor, and this we are done. Now we're done with step 7. We have computed the benchmark case in 2010 for the United States. Now, if you want to extrapolate our results to the year, let's say 2050, you have to change this a little bit. You have to adjust the code, so you need to load beta 1. Just use our calibration of beta, because beta is a deep parameter. So there is no good reason why, for example, beta should be different in, let's say, 30 or 40 years. We have learned this from Lucas and his rational expectations revolution. So if you want to compute, let's say, the Laffer curve in 2050, you use the demographics from 2050, which are provided above, but you use the old beta, which we calibrated, because this deep parameter will not depend on demographics. And in the final step, we compute the Laffer curve as a function of the wage tax tau n. We store the results in the matrix results, and we compute the solution from SS aggregate, which is our function that describes the complete model with all endogenous variables, including the aggregate variables, but for our constants beta now, which we have calibrated, so we will not adjust it. And for this case, we just computed for different values of tau n, store our results, so compute here the wage income tax as the product of tau n times the wage rate V bar times aggregate labor N bar. And we also compute total taxes, so also include consumption taxes and capital income taxes, and display it as a function of tau n plus tau p plus, so wage tax plus social security contribution. And this terminates our computation. So I just press continue so that the rest is computed and that our solution will be displayed shortly. So our Laffer curve, our total tax income, and our wage tax income as a function of total taxes on labor, including labor income tax rate tau L and pension contribution rate tau P. And we have nice hump-shaped functions which maximum at around 65% for total taxes and around 70% for the labor income taxes. So in conclusion, let me thank you for all your patience on keeping up with me here through this presentation of the MATLAB code. If you have any questions, please do not hesitate to send me an email, and I will try to answer it as soon as possible. So I get a couple of emails, so this might take a while, but I hope you have enjoyed it, and good luck with your programming. So try to rewrite the program code that you can use it for different time horizons. See that the fiscal space will shrink in the United States over upcoming decades due to the demographic transition. And I hope you find this kind of economics interesting. So thank you and good luck.